Good day. My name is Lunghile, and today I'd like to present a solution to one of the problems that are presented to undergrad students, which is the design of a heat exchanger. So it's mainly part of either your plant design course or your equipment design course. So just to give you a bit of background on why I'm doing this and the motivation behind it, since I became an engineer, one thing that I realized was tools like this, where students are given a sort of guideline in terms of how to go ahead with their design projects, are something that are quite rare to find, especially for students that are doing self-study. So over the years, I've worked with a couple of students, undergraduate, master students, recently even PhD students, to assist them with their design projects. And while doing that, I myself discover new ways of doing things. And what I like to do is to put them in document form, in template form, so that other people can be able to use them. So that's basically what we're going to be doing today. We're going to be looking at the heat exchanger design. So it's a simplified heat exchanger, but it should give you the concept and how to go about, designing your own heat exchanger. So what I'll do now is I'll just share the screen so we can get started, and we'll go through the different stages, starting with calculating your heat duty, then going on to your estimating your heat transfer area, and going on to calculating heat transfer coefficients. So what you need to do as a student, obviously, is you cannot just rely on the guideline that I give you, right? The most important thing is to go through your textbook, is to understand with this particular presentation, I won't go deep into the details of the method we're using, how it was derived, whereas for you as a student, it's important for you to go through this thing so that you have a deeper understanding of what you're doing. So let's get started. So our design objective today is to heat up a reactor feed consisting of 95% ethanol and 5% water from 330 degrees, 330 Kelvin to 423 Kelvin, right? So the pressure is 5 bar and the flow rate is 0.17 kilomoles per hour. So this is just a random design question based on some arbitrary design project from one of my students. I just created it so that I'll be able to take you through the steps. Now, one thing you want to do is you need to get into a habit of being formal in terms of your annotations, in terms of your equipment numbering, because that will help you when you get to the heat, to things like PNIDs design, PFDs, your documentation of your work. Because what that helps is in the future, especially if you end up in a design environment as I was in, that will help you a lot, because design is mainly about cataloging and documenting. You do a lot of literature review, and you need to be able to document the literature that you read, so that when the design comes and you need to grab certain information from certain sources, you're able to find it. So get into a habit of cataloging your work properly. So one thing, process side, we've chosen to put in what? The ethanol and the water, and then on the shell side, we're going to put in the high pressure steam, right? So that's the heat exchanger we're going to design, and I'm going to take you through how we will do that. All right. The first step, obviously, is determining the heat duty, right? So there are two ways of doing it, right? You can calculate it manually, or you can put it through a system like COCO, right? COCO, which is a simulator, which by now, if you're doing a plant design, especially third year level, you should have been introduced to a simulator. So the first thing you'll need to do is calculate your heat duty, right? Manually, the formula we'll use is what? Q is equals to number of moles, Cp delta T. If you're using number of moles, you must make sure that your Cp is given in what? In joules per kilomole Kelvin. Whereas if you're using mass, you must make sure that it's given in joules per kg Kelvin. Just be careful of unit operations. This is something that I will be emphasizing a lot during this design, because the one thing that happens is you end up getting unreasonable sizes on your equipment, and you're surprised, where did that come from? And one of the reasons you will have the challenge is not paying attention to your units. That is very important. So your unit conversions are critical in making sure that your design comes right. So in the case where you calculate it manually, so you have your flow rate, you have everything, this is how you get your heat duty. And what you'll come to is the answer will be 225,403 joules per second, right? And then what we'll then do is, if you go back here, I've created this is the template I was speaking about that can be available to you if you want to use it. The whole point of this template is to, one, have it available if students need it, and two, this video will help you be able to navigate through this template so that the work that you do is your own work, and the template is just simply a calculator that you use to punch out the numbers. But the one thing is, it is not a shortcut to your design project. This is just a tool that you can use to work faster. And it's important that you also learn how to develop such spreadsheets, because design work is mainly about creating spreadsheets that will make your life easier. So one thing you'll see here is, now we've just calculated the heat duty, right? So this is the actual heat that is supposed to be transferred from one fluid to another. And then when you're cooling, it moves from where? It moves from the hot fluid. It's always, when you're cooling, from the processed fluid to the utility fluid, and the opposite happens when you're heating, right? And then, so a utility fluid is the fluid that is used to change the state of a processed fluid. So, so for example, if you want to heat something up, you'll get a stream that is hotter than that stream. That stream is called the utility, right? And then let's continue. Now, before we get anywhere, right? The next step that comes after that is estimating the trial U value, which is the overall heat transfer coefficient. Now, let me just take you through a few things about that, right? So the heat transfer coefficient is the sum of all resistances, right, of heat transfer. So basically, if you were doing conduction through an electric wire of electricity, your overall heat transfer coefficient is similar to the properties of the metal that electricity is flowing in that resist your flow of electricity. So your overall heat transfer coefficient is basically a total, right? It's all the layers, right, of conductive material or non-conductive material, because obviously it can be completely non-conductive, of course, but it's a collection of all those layers that will reduce your overall heat transfer, right? And this includes the heat exchanger walls themselves, and it expresses K. So if the material you're using will have a conductivity, that is how much heat transfer to allow through. You will also have fouling factors. This is if you look at inside a kettle, when you're boiling water, you see it will start accumulating a layer of flaky material. That's the same kind of material that we're talking about when we talk about fouling. And then lastly, you look at the properties of the fluid itself, where a fluid will create a film if it's moving against a certain surface, and that film will also create a heat transfer barrier. So this is the equation that we are trying to get as the first step to designing our heat exchanger. And just to jump ahead a bit so that you have a general understanding of where this comes in, right? I'll come back to the equation above, but basically when you calculate your heat transfer area, it is heat duty is equals to your overall heat transfer coefficient multiplied by the area multiplied by delta T mean, by the mean temperature difference. So the whole idea is we are trying to get that overall heat transfer coefficient so that we can calculate the total heat transfer area. So let's go back and be systematic in terms of our procedure. So first step is you need to understand what your overall heat transfer coefficient does, and that you can do more reading. So to get started, the first thing we're going to do is we're going to estimate an overall heat transfer coefficient. Why, right? The reason for that is initially you need to be able to get started with your calculations because the overall heat transfer coefficient opens up your path in terms of being able to calculate everything else, right? Just up to the pressure drop calculation. So it's the first thing, it's the first value you need. And in order to be able to do that, you need to be able to estimate it. So if you go to your design textbook, you'll find this particular table where it has the surface fluid coefficient on the bottom, and it has the process fluid coefficient on the top. And then the line here is your estimated overall coefficient. So the whole aim is to be able to join, right, your surface fluid coefficient with your process fluid coefficient, right? And the way it intercepts the overall the overall coefficient, that is the value you're going to be used. So because we're using condensing steam, so between 4,900 and 4,500, and then I chose to choose that point, and then you draw a straight your surface fluid. So we're dealing with what's it? What is our with? We're dealing with ethanol. We're dealing with ethanol, which is a light alcohol, which is an alcohol. Let me see if we are in the region. So so I placed it with the paraffins, which could be a bit wrong. It would be more suited in the region of your boiling organics, but you still come out to around the same number, between 800 and so. So it's important that you identify your process fluid properly. I had placed it under paraffins, which is something you can correct. It's an estimate at the end of the day, but it's important that you start off at the right estimate because the method we're using is iterations. And the one thing that can make an iteration go wrong is having a wrong initial starting value, which will throw off your numbers quite significantly. Okay, so we're going to use our trial value of U of 800 watts per meter square Kelvin. So before we even proceed, let's go to our workflow worksheet. And if you come here, you will see that already the template has been highlighted where you need to put in values. For example, we've just calculated the heat duty. This is where you would put in your heat duty. Your trial value, we just said it's 800. So let's punch in 800. And then we go up and we then put in our heat duty. And we said our heat duty, we're gonna assume that my calculations here were okay. And our heat duty is 225,403 joules per second. 225,403 joules per second, which is what, right? I think there was a 0.03 at the end. Then we allow that in. I'll assume it's not allowing us through because of the formatting of the number. Okay, now that's fine. So now we've got the first starting point where you put in your heat duty and then you just punch in your estimated U value. Next, we now come to calculating the mean temperature difference. So the way this spreadsheet has been designed is that in order for you to get answers, you need to be able to input the correct data where it is required, right? So let's go to the input data. So before you even continue, what would be critical is for you to fill out this complete table, right? And in order to do that, right, as I indicated before, I use Cocoa Simulator, especially because now you want to get the densities, the viscosities, the capacities of a mixture, which you could get manually if it was a pure substance. But the problem now is you've got a non-pure liquid, which is 95% ethanol and 5% water. And the problem that creates is now you have to do a whole lot of calculations involving averages and all of that. Whereas putting it through a simulator, it will just give you a quick answer. And when you watch my other videos that deal with simulators, you'll be able to see why So the next step obviously would be to fill out this table, but just so that we go step by step, let's complete the information that we have already, that we got as part of our design problem, right? So I'll just go down slightly. For example, we know that our flow rate is 0.174 kilomole per second. So that I can fill in 0.174. And because this is a non-reactive process, the number of moles coming in will be equal to the number of moles coming out, right? What else do we know? We know that our process fluid is coming in at 330.83 Kelvin and leaving at 423.15. So that we can already put in 330.15, and it is leaving at, let's go back, make sure we got it right, 423.15 Kelvin, 423.15 Kelvin. So it's coming in at 330.15 and leaving at 423.15. And then the one thing we can also calculate, of course, is the shell side, because we're using steam. So the one thing you need to be careful here of is before you do anything, you need to understand how approach temperatures work and the difference between counter current heat exchange and the difference between counter current heat exchange and what's the word I'm looking for? Counter current heat exchange and counter flow heat exchange. So the heating fluid is condensing steam, which will be on the shell side. The steam enters at 433.15 Kelvin, 6.6 bar. Using an approach temperature of 10 Kelvin, then you take the difference between the steam and the cold fluid, and you put that at 10 degrees at 10 Kelvin. What that will then do is it will give you the value of the exiting steam, right? The other way to do it is, especially for counter current, where counter current does not have a challenge of overlaying, of crossing, where the overlaying or overcrossing, where the process fluid temperature crosses with the heating fluid temperature. You would then have to look at that. As I said, you need to take time to go through the whole approach temperatures and how counter current and counter flow works, right? So what you then get is that your steam coming in is at 438.15 Kelvin, and your steam coming out is at 428.15 Kelvin. So I'll go back and put that into my input data, 428.15, and your exit stream is now this was 438. So 438.15, and your exit stream is 428.15, right? And then I had a few notes for you here. And once I've punched that in, it should immediately be able to calculate for you the log mean temperature. And so that is the one step. The first step you need to take before you calculate the mean temperature is you need to calculate the log mean temperature. So let's go back to our template and see how far it's taken us on the information we have so far. As far as I know, everything should be calculated by now. So let's go back. So as you can see, because now we're putting our temperatures, it has given us the value for our log mean temperature. And that's the formula up there, which is the same formula as we have on the spreadsheet. And if you come here from your design textbook, you will see that there are two constants that you need to calculate in order to be able to evaluate the formula for mean temperature difference, which requires you to have a factor, which is FT. Let's just go back. So FT is the temperature correction factor. So in order to be able to calculate that, you need to have these two constants, which are given by the two equations here and here, right? As again, make it a point to revise the definition of approach temperatures in your lecture notes, and make it a point to read your design textbook regarding the origins of the temperature correction factor, right? And these are your formulas. And based on the information we have so far, our spreadsheet, as I know, it should be able to take us as far as your mean temperature, which is here, 60.85. And this will need to be corrected. It still says log mean, but it should be just mean temperature. And if we proceed, you will see that we now have all the information we need to calculate your estimated heat transfer area, which is 4.62. Now, let's go back to our spreadsheet. If you see here, must be an error somewhere because that's giving us 60.71. I'll just need to review that. But again, please note this is not your final answer, as this is an estimated U value. So let's go back to the template and see where the error may have come from. Just hold on. $225. Just want to make sure that our initial heat thing 225,403.07. 225,403.07. Just want to make sure that those values are correct. So we've got number of moles, we've got the CP, which is 1,404,486.12. We've got the temperature difference. Just want to do a quick calculation, make sure that our heat transfer is okay. That's not the area I was expecting, hence I'm a bit skeptical. It's always good to check your work, because numbers never lie at the end of the day. Just hold on. 1.738 multiplied by 140486.22. Then we'll multiply that by 92,316. That's 2.25 million. So there was an error here. There was a definite error here in terms of the value. This was actually supposed to be 2254,034.07. And that gives us a starting value of 46.29 meters squared. So we can then go back and correct those values. So this was supposed to be 2.2 million. So you must always be careful in terms of how you present your numbers, because that can create an error going forward. So if we go down, then up to so far, our calculations have led us to an estimated initial area of 46.29431. 46.29 meters squared, right? So far so good, right? Without having to do any simulations, we are able to get as far as estimating the total area of the heat exchanger. Now, you'll see later when you're doing your plant design that you'll be required to give, for example, the costing of the total plant, where you'll find that you only did the design on one heat exchanger. That means that if your plant has maybe 5 heat exchangers, you will need a quick way to estimate your heat transfer area. And this is it. So this spreadsheet that I've designed for you here allows you to do that. And at the end of the lecture, I will discuss what you need to do to get this template, because it will be for sale. And for students who contact me through after watching this video, there will be a discount on it. However, we will discuss the price at the end of the lecture. So now we've gone as far as calculating our area. Now we need to do the exchanger layout. And in order to do that, we need to determine the number of tubes, the bundle diameter, the bevel spacing, and the cross-sectional area. Now, it is important that you do additional reading on the different types of heat exchangers, because the above that we've just mentioned now are dependent on the type of heat exchanger you are using. For example, in this particular design, we'll be using a fixed U-tube exchanger with 2-pass triangular pitch. Now, that in itself will determine, will make a huge difference in terms of how our heat exchanger will work. So these are your dimensions for steel tubes. So if you go back to our next step, what we need in terms of our information is what? We need to get our outer diameter, our wall thickness, our inner diameter, and that will help us calculate the tube length, right? So, also our tube length. And then what we'll then do is we'll be able to get our number of tubes and everything up to, by doing that, I believe we should be able to go straight down up to area once we put in our clearance as well. So let's go get that information. Now, for this one, I've already put in your input data here. So as you can see, you've got your wall thickness in millimeters. So it first wants outer diameter, which means if your outside diameter is 16, let's see what we chose for this particular design. We said our outside diameter was 0.025, and you need to do that unit conversion as well again to make sure that it's fine. So you need to divide by 1,000. So we'll do that on the spreadsheet. We'll take 25 and divide that by 1,000. And now we'll have our outer diameter. And then if you go back to the very same table, it will tell you that if you are using 25, then your wall thickness is what? Is 1.7, right? So if your wall thickness is 1.7 mil, then what you need to do is, again, you go to your wall thickness, go back to our table, 25, you divide that by, again, 1,000. It's important that you don't forget your unit conversions. Therefore, your inner diameter will be your outer diameter, subtract your inner, your wall thickness, and now you have your inner diameter. Now, tube length, let's go to our notes. With the tube length, what we did was the range starts from 1.83 meters to 7.23. Again, this is in your textbook, right? And then the choice of tube length has the following effects. Now, long tubes reduce tail diameter, which in turn reduces the cost of the heat exchanger. But that will obviously come at the cost, because this will lead to a bigger pressure drop, thus increasing the cost of the pump work. So design is a give and take situation. So your optimal tube length to shell diameter ranges between 5 and 10. And you'll see later when you use this range to be able to determine whether or not our heat exchanger is within range. And we will take our estimated tube length to be 3.66, which is between those two values. Let's go back and punch that in. So now we'll punch in 3.66. And you'll see it will immediately give us your number of tubes, immediately populate your bundle diameter. And once you have that, because everything up to here depends on the information that we've given upstairs. And immediately after that, you'll see that you'll be required to provide a clearance. Now let's go back to our notes. So the guideline, this heat exchanger design document, is designed in order to be able to take you through exactly what you need to do and how you do it. So by the time you finish studying this document and practicing how to do the actual design, you will be able to do your own design, no matter the type of heat exchanger you use, because the methodology is almost the same for all of them, and no matter your substances. Again, so this is how you determine your clearance. So what you have at the bottom is, can you get this table from a design textbook? You have your bundle diameter and you have your shell inside diameter, right? Now, if we go back, what are we looking for? We're looking for the clearance. So what you then need to do, so this is your clearance, shell inside diameter. So that's your clearance, right? So shell inside diameter to bundle diameter. So that is the clearance we're talking about. So what you then do is you take your bundle diameter, which you already have, you move in a straight line up to the fixed and U-tube, and that's the one that we said we're using. And then you go in your straight line up to your shell side inside diameter to bundle diameter. And as you can see, if we're moving from 10 to 20, that should be sitting at around 13, 14. So we come back and then we input 13. Once you've done that, you'll see that automatically your spreadsheet will take you as far as your cross-sectional area. And if we go back up here, you'll see that we are almost on our way home. Now, here's the problem. Now we're almost done with what we've inputted so far. Your spreadsheet should be able to calculate everything else in this scenario up to where I've highlighted in green. The reason it's not able to do that is because you haven't inputted your what? You haven't inputted your process information. So let's go back to input data. So now we need to fill out this whole section in order for us to be able to do what? In order for us to be able to complete our simulation, right? Not our simulation, but our heat exchanger design. Apologies for that. Okay, let's go. So as I said, this can be done manually. You can get information you can go to tables like your Paris handbook, chemical engineer's handbook. You'll get all this data that you need. You just need to make sure that you're working within the right temperature ranges. Otherwise, you can use a simulator. So let's get started. What I'll do now is I'll go to Cocoa, and we just need to remember what stream was simulating. So I'm just gonna shoot back up, and it's 95% ethanol and water. So if you've used Cocoa before, I won't dwell too much on this. We do have a course on, we do have a video on YouTube, on our YouTube channel that deals exactly with this. So please go there if you're still a bit rusty on Cocoa. And of course, don't forget to sign up. So I'm just gonna do it quite quickly, just to show you how we get the information. For an in-depth lecture on this, you can go to the Cocoa website to check it. So we can give it a title, and we can call it our HX design. And then components, we will need just water and ethanol. There's our water. Let's add it. And we need ethanol as well. There's our ethanol. And then from there, we go to properties. Then you just need to choose the right. Here we can just use Antoine, and then use. Again, for a better understanding of this, we'll go through some of our simulation videos. It will explain to you where to get the thermodynamic models and the understanding of where they come from. Let's close that, and then we go back to our simulation. So again, this is the shortcut way of doing it. It is possible. I remember when I was doing my first heat exchanger design, it was at the Feds, we had to estimate these properties. So let's put in a heat exchanger. So again, we're gonna simulate what we're calculating manually that side, so that we understand the process conditions coming in and leaving the heat exchanger. Right, and what needs to come in here is, we said we're operating at 5 bar, so I'll change that to 5 bar. 5 bar. Our stream is coming in at 330.83. Let's go back to the simulator. At 330.83 Kelvin, right? And the mole fractions we have, syntax error, it means it's not using the same format as our, so it's set on as the value. We said we were coming in at 330.83, 330.83. Excuse me if I'm rather moving quite fast. I'm recording this on Zoom, so as you know, Zoom has a 40-minute limit. So I want to make sure that we cover as much as possible. At 5% water, and let me just confirm that, and 95% ethanol. That's given us, and then our flow rate was given in kilomoles per second, and that flow rate was 0.174 kilomoles, not 0.174 kilomoles. And then we know that our heat exchanger, we need to heat up the stream to 423.15. We need to heat it up to 423.15 Kelvin. So our outlet temperature will be 423.15 Kelvin. Close that, and we run it. Now, once you run it, you'll be able to have all the information you need, because if you double click on that, you'll see you've got overall properties where it will give you the enthalpy and all of that. But then you also have here where the incoming stream, first of all, you need to check. The incoming stream was fully liquid. So if it's fully liquid, it means the information you have will be on liquid properties, right? So if you drop down liquid properties, you'll now be able to get your information. Just a few things that you need to make sure your units have to be similar. So make sure your viscosity is in Pascal seconds. Make sure that your, let's go down, your CP is in joules per mole, because that's what we worked with initially. So what we can do to check that is, if you check everything is in kilomoles, let's see initially. So we said the CP here should be in joule per moles. So it's important that you use joule per moles on your CP. So let's go in. Let's put in our data. Oh, already the spreadsheet shows you what units you should be using. So follow the units as they are on the spreadsheet. So first thing, we'll pick up our density. So our density here happens to be given in moles per meter cubed. We want it in moles per meter cubed, so that's the right value. So you can, doesn't allow you to copy and paste. So let's just write them down. 177. Let me see if it doesn't allow you to copy and paste. It should. Okay, it doesn't. So 17774.51. That's the first value. 17774. So let's be careful not to put that in the wrong place. It's coming in the 17774.51. That's our density. Let's make sure that's correct. 17774.51. Yes. The next value we're looking for is our viscosity, and that will be 0.0006. 0.0006. That's our viscosity. 0.1236. Then our heat capacity. Our heat capacity down here is 145.09. So our heat capacity 145.09. And then we need our thermal conductivity. 0.181. 0.181. Put that in 0.181. And then your phase fraction is 1 in this case. That's why I won't input anything on the vapor side. And then your molecular weight just confirm that it's given it to you in the right units, kg per mole. We need it in kg per kilomole. Hold on. We need it in kg per kilomole, which is 44.6. Let's go back. 44.6. Again, highly critical that your units are exactly as they should be. And then now we're going to our outlet stream. That, double click that. And again, now you've got a vapor fraction of 1. So which means all your properties will be in the vapor phase. So let's get started. Again, our molecular weight is 4.66. So that hasn't changed. So outlet stream 44.6. And we've got a phase fraction of 1 in the vapor. Let's go look for thermal conductivity. Our doesn't give a value for thermal conductivity. Okay, so you leave it as it is. And then we're looking for density, which is 142.11. Density is 142.11. And then your viscosity. Viscosity is 1.25 times 10 to the negative 5. 1.25 times 10 to the minus 5. One copy there because I haven't said it equals 2. Right? 1 times, oh, I see. 1.24 times 10 to negative 5. So it should give us the same value, yes. And then our heat capacity, CP is 85.315. 85.315. 85.315. And then our thermal conductivity. Thermal conductivity, as I said, it was not given on this particular one. So which means that when you're doing your calculations, if it ever requires you for a thermal conductivity, you'd use the liquid. Now, let's go back to our spreadsheet. I know we still need to do the shell side. I just want to give you an idea to show you that most of the values should start opening up. So let's see. You see that some of the answers are starting to pop up. So this one needs this particular CP. We're dealing with the shell side. So this particular CP is of the bottom of the steam. So again, we need to fill out this section. And in order to do that, we need to do a new simulation, but now just water. So we're going to click new. And then here in our properties, we'll add, and instead of jumping to ChemSep, let's just do the water one now. Assign property package, close that, and again, run it through a heat exchanger. So as you can see, we're doing the two separately. You can do them on one simulation. It is actually quite easy to do, but again, it needs you to have a proper understanding of your approach temperatures and all of it. So this one is quite easy to do. We said our steam is at 6.6 bar. 6.6 bar. It's coming in at a temperature of, let's go back, of 438.15. 438.15. And then the properties we're looking for now are not really dependent on how big your stream is. 438.15. And then we're going to do, let's go to kilomoles just so that because we're used to, and let's just work with 1 kilomole. Then What we'll then do is define our outlet temperature, which is 428,15. 428,15. We run our simulation, and we should be able to get all the information we need. So look at that. So again, we're gonna take the values we need. Let's change that to what we're used to. Okay, so let's start density 191,105. Density. So coming in, it's just vapor 191,015. And next we look at the viscosity, which is 1,44 times 10 to the negative 5. Viscosity equals to 1,44 times 10 to the negative 5. Right. Next is heat capacity, and our heat capacity is 44,47, sorry, 44,47. Next, our thermal conductivity. Our thermal conductivity is 0,032. 0,032. Phase fraction here we've got 1, and then our molecular weight is 18,01. 18,01. It is water after all. 18,01. So that's fully defined in the input, and then output. We should have 2 fractions. Phase fractions, but only liquid. So our density is 5643.103. 5643. So out, we're gonna put in the liquid side, 5643. I'm just gonna go through this quickly so we can get to the whole point of this. And then our viscosity is 0.00017, not 0.00016. And our heat capacity is 77,88. 77,88. And our thermal conductivity is 0.683. 0.683. Phase fraction 1. Molecular weight, again, obviously 18. 18,01. Now, let's go back to our calculations. We've populated most of the information, and now you go back, you see that in the calculated your mean simply for the shell side, it will give you the your hot and cold heat. The heat lost by the hot stream is gained by the cold stream. Therefore, you're going to be able to calculate the amount of water you need for that kind of cooling, which is 66.37 kg per second. This will give you the mass velocity of your shell stream. From that, you'll be able to calculate your shell equivalent diameters, which will give you the Reynolds number, Prandtl number, and finally be able to calculate the Nusselt number. We'll go back to the worksheet, to the Word document. I just don't want to run out of time. Just want to show you that with just the information we've populated so far, we are able to get as far as your all your heat transfer coefficients, and the only things that we're missing will be your what? Will be your factors, which is HOD and HID, and your conductivity of your steel. So let's go back to our spreadsheet. So far, as you see, it's almost completely populated. Now we can come back to our Word document, And as I said, I do have to rush through. You have seen the gist of it in terms of how it works. So your Word document will give you a step-by-step detail in terms of how everything is done. As you can see, you have to assign your fluids. It will give you the formulas. It will show you how everything is derived, giving you explanations as we go, where to read, what to follow up on, how to get your heat capacities, so property tables or using a simulator, which is what we did. I'll take you on to how to calculate the Prandtl number, bit of information on what it is, but as I said, most of that stuff is found in your textbook. It will proceed to how to calculate the Nusselt number, and again, this is, and then for the truth side, it will also give you the formulations on how to do that, and in terms of everything that's there. And finally, you get to this table, which will give you your typical fouling factors, and we are using condensate steam, which is between 1.5 and 5,000. So for that one, let's take somewhere in between. So let's just make sure that we assign the right ones, right? So these are typical fouling factors. So what you'll then do is next, the heat transfer coefficient HI is 26.16. So what would, from the table above, we can show that the estimated fouling factors. So for the shell side, which is the steam, HOD is 2.5. So just take that directly from the table, right? 2,500. And then next, from the table, we took ID as 5,000. And then finally, we need the conductivity of the metal. And in this particular case, we're working at about, so you look at your temperature ranges. So it will tell you that, for example, your brass can go up to 400 degrees. And then your carbon steel can go up to 260 degrees. In our case, we are working at the highest temperature we're working at. Let's just go back to our table. It's 423 Kelvin. So if we take that and minus 273.15, 155. So if we go back to our table, we can see that carbon steel could be suitable for this, aluminum could be suitable for this. So depending on which comes cheaper, you will then choose that. So for now, let's just go with carbon steel. So with carbon steel, if you're working at the range of about 100, your conductivity is 58. Come back here and come to our spreadsheet and we input 58. What that will do is it will then calculate your new U value. Now, if you remember, the initial U value was an estimate, right? So what we need to then do now is we need to take that U value, copy it, and then come paste it as a value on the estimate. And what you'll see happening is that things will start changing. Your area, for example, now is smaller, right? There's a place where we put in a calculation of L over D, which is your tube length over your shell diameter, 9.17. It's between 5 and 10, which means our exchanger is working in the approximate right area. And we then come back to check our U value is now 1236.69. We then copy that again and compare it to the one we have here. So again, you pick the number. Now it gives you 1236.69. You go back to your new value, you copy that, and you continue doing this until the numbers converge. And what do we mean by converge? Until the numbers, until the estimated U value, the trial U value, and the new U value are exactly the same. Let's go back again. Now they are the same. And then from our L over D is still below 10. Now you come back to your instructions. That's actually it for this lesson. And one challenge that I put in for you is what you then need to do is obviously you'll be able to populate you'll be able to put in your new value. This was based on that particular estimate value that we have, but you'll be able to calculate your final U value. And in our case, it was 1,200. And then what I have here is just a few notes for you. For example, the importance of using Excel, especially when it comes to iterations. So it is quite important for you guys to using things like Excel, because one, it allows you to do iterative calculations quicker. And then what I'd like you to do now is to use the skills that you developed here to check that you should then come back to the spreadsheet that we have. And these are the different ideas that you can use to see if it works. So that's it for today. I hope the lesson was quite informative. Of the day, the aim of it all is to try and help students to get better results in their studies, and to also have a broader understanding of the discipline of chemical engineering, as there is so much in it, especially engineering design, which is a personal favorite of mine, because of the flexibility and the fact that plant design is one thing that we as chemical engineers can say we own, because it happens to have that one section called reactor design, which only we can do. So enjoy your studies this year, guys, and I hope all goes well. Cheers. Bye-bye.